Okay. I'm slowly going to start, I think, with this session on, there's some singing around, but it's not me, about Interdomain Layer 2 Network Services and Experiments. I think the title is a little bit fake, quite open. You also will see different subjects, VPLS, Ethernet, and GMPLS. So it's almost the whole stack will be discussed, but yeah, you always have to decide on a title, and this was the title for the whole session. So. But we start with VPLS. I think there was already a mention earlier by the event about VPLS services. So I think it's normally people are a little bit afraid of going to VPLS, so making a local area network over a wide area network. But it's nice to hear more people thinking about that idea, and Laura Serrano from RedIRIS is going to say something about that, what their experiments are in Spain. So I would want to give the floor to Laura.
Okay, thank you very much, Victor. Hi all, can you hear me? Yes, no? As Victor had just told you, my name is Laura and I work as network engineer in RedIRIS, Spain. During the last year, we started to work with Layer 2 VPNs, firstly point-to-point, and in fact, we provide this service to our customers since the end of the last year. But considering the recent increase of the requests received from the customer, we thought that it would be interesting to do some kind of test for multi-point service. In this sense, we have been working in RedIRIS and in collaboration with people from CESGA, another autonomous region, another autonomous system in Spain, in order to put in production VPLS between us for testing purposes. For us, the main goal of this test was to familiarize us with this new technology and its configuration, and to verify the impact that the process to put in production VPLS could have over a production network. Okay. Very quickly to introduce ourselves, RedIRIS is the national research network in Spain, and it joins more than 250 institutions, research institutions. And the other autonomous system involved in this test is CESGA. CESGA is the supercomputing center of Galicia, one of the autonomous regions in the north of Spain, and it is the responsible to manage the regional research network in this autonomous region. This is the index for the presentation. We will review very quickly the main concepts of VPLS and the configuration steps for intra and interdomain environment, highlighting the scalability properties. And finally, we will see some possible application of this technology. Okay, what is VPLS? As you probably know, VPLS is one of the most innovative ways to provide Ethernet MPLS virtual private network, and one of the solutions offered by MPLS. I mean, there are three kinds of VPNs offered by MPLS: Layer 3 VPNs, Layer 2 VPNs for point-to-point service, which follow the specification from Martini and Compeladráp, and Layer 2 VPNs for multi-point service, or VPLS. With VPLS, the provider network appears as a single LAN. I mean, when a provider edge router receives a packet, if the destination MAC address is known, the packet is directly sent to the remote site. But in other case, this packet is sent to all the remote sites. So in this way, the provider edge router learns the MAC addresses from the packet it received and allocate this information in a new table. With respect to the standard, there are two alternatives to implement VPLS. The main difference between them is that the first one uses BGP as signal protocol and is supported by Juniper, and the second one uses LDP and is supported by Cisco. In our case, we have selected BGP as signal protocol. Why? Okay, theoretically there are a lot of benefits to use BGP as signal protocol because BGP is an inter-provider protocol by definition, so if you use it to implement VPLS, you can take advantage of the scalability properties BGP offers you. But there are another important reason in our case to select BGP as signal protocol, because we have Juniper boxes, so there isn't another possibility. Very quickly, only to remind you that when we speak about VPN configuration, we should have in mind the feature of 3 different devices. The customer edge, which is a router or switch connected to the provider network. The provider edge router, which maintain the VPN information and exchanging with the other provider edge routers, and which is the responsible of the MAC addresses learning process. And finally, the provider router, which forward the traffic in a transparent way through the network. Okay, let's go with the configuration steps. For this case of a study, we wanted to connect 3 customers or 3 sites connected. We wanted to connect 3 sites with 1 VPLS connection. In this picture, you can see the topology of RedIRIS network and the location of each site, and you can see 2 of them are connected in Madrid, and the last one in Andalusia. But all of them are in the same domain, so we are speaking about intra-domain environment. Basically, there are 3 steps to configure VPLS. Firstly, we need to advertise the VPN route, and for this purpose, we use a multi-protocol BGP session between provider edge routers. After that, in order to advertise the internal route, the loopback addresses from each provider edge router, we will need a full mesh LSP connectivity between provider edge router. For this purpose, we can use RSVP or LDP, as you prefer. In case you use RSVP, you need to configure manually in each ingress router. And in case you use LDP, you will have LSP connectivity among all routers. And finally, we need to configure 1 instance for each site. In this feature, you can see the router involved in the sample described before, in which you can see that we have 3 sites connected to Iris 2, Madrid 0, and Sevilla 0, and that we need a full mesh multi-protocol BGP and LSP connectivity between all these 3 routers. The result of this configuration is that we have 3 customers physically connected over a layer 3 network as they were in the same LAN. They could use private addresses and communicate between them as they were in the same room. In this case of a study, we wanted to connect as before 3 customers through 1 VPLS connection, but in this case, 2 of them are in RedIRIS domain and the last one in the Tesla domain. So we are speaking about inter-domain environment. For one first approach, the configuration steps are very similar than before. To advertise the VPN route, we need to configure a multi-protocol BGP session, but in this case, some of the session will be external and another internal. And to advertise the loopback addresses, the internal route, we need a full mesh LSP connectivity between provider edge router. For this purpose, we could to extend the LSP from each PE to the others manually, and to configure a normal BGP session between autonomous system border router. But there are another possible more scalable solution, that is to use a new family called label unicast, which result in label route exchanging between an autonomous system border router, which establish LSPs between PEs. In this feature, you can see the configuration that we need to add with respect to the last example. Basically, we will need a multi-protocol, external multi-protocol BGP session and BGP for label in UNICAS. The result, as before, is that we have customers physically connected over a layer 3 network as they were in the same LAN. But moreover, from the provider point of view, we have an IPv4, IPv6, IP multicast, and VPLS traffic with exactly the same infrastructure and without any interaction between them. And from the customer point of view, we get more security and flexibility because only trusted hosts are included in the VPLS connection. And moreover, the customer manages each network without provider control. In this graph, you can see an example of a real transfer of information between two customers connected through this VPLS infrastructure using ePerf. Okay, but what happens if we want to add more extra site? If you remember at the beginning of the presentation, I spoke about the benefits to use BGP with respect to scalability properties using root reflector. If we have a root reflector, we will only need one multi-protocol BGP session between domains, concretely between root reflector, not between provider edge routers. I don't know if this idea is clear. To clarify all these concepts, when we speak about interdomain VPN configuration, we have three level stacks. The first level is the VPN level, and for this level stacking we need a multi-protocol BGP session between root reflector for the appropriate family. Layer 2, Layer 3, VPLS is exactly the same idea. The middle level is used by the autonomous system border router to associate the packet with the LSP leading to the next autonomous system border router in the path. And for this level stacking, we need to configure a BGP session for labeled UNICAS. At this moment, we have the general inter-provider VPN configuration. So if we want to add more extra site, we will only need to extend the current level stacking from the root reflector to the final provider edge router. And finally, the top level is the MPLS level and is used to associate the packet with the LSP connecting the autonomous system border router with the provider edge router, and is assigned by RSVP or LDP. And that is all. Well, I would like to remark some important consideration in case you configure VPLS with Juniper buses. The first one is that you need a tunnel PIC for each provider edge router, and that the technology in both ends of the VPLS connection must be the same. I mean, Ethernet or Ethernet with VLAN tagging. In case you want to have different technologies, you need to have a QPP PIC to do the translation. And well, and of course, because we are speaking about external BGP session, it's important that you have in mind the next hop value, and don't forget to put the no next hop change statement in the configuration. And here you have some useful command to verify the configuration. Basically, you need to verify the state of the BGP session, the information exchanging between peers, the LSP's state. Okay, but really the question is, why VPLS? In this sense, we have been spoken with our customer in order to know in which way VPLS could help them. And we have received some interesting input from them, especially with respect to two areas. The first one is grid application, because in Spain there are a lot of supercomputing centers. And the second one is the Opera Oberta project, one of the international projects in Spain. With respect to grid application, some of the problems that could be solved or reduced using VPLS are the following. The first one is the routing itself, because grid systems are very sensitive to delay variation, so even routing changes can be dangerous for the stability. The second one is about the security problem, because when you join multiple computers to get a single machine, and all of them can be reached from external links, the new system can be attacked from a lot of access points. With respect to the efficiency, well, when you configure two different computers as a single machine, it's normal that you want a link as transparent as possible between them. And finally, in case we have VPLS infrastructure, we could use some useful Layer 2 tools, as for example, BootP, WebLAN, or even to install applications in remote hosts without using FTP, for example. And thinking on VPLS as a good way to solve or to reduce the grid application problems, why doesn't extend this idea to the big ones project, as for example LHC? Okay, this is an idea to thinking about in the future. Why not? The other application example is with respect to Opera Oberta project. Opera Oberta project is an international project in Spain consisting on a high-definition retransmission of Opera by multicast for IPv4 and IPv6 protocol. And at this moment, there are more than 50 institutions participating in this project from different domains. So with respect to security problem, the private keys to encrypt the Opera retransmission and send it using the IP network. So VPLS could be a good solution for the problem, from this problem, no? But moreover, we could use a VPLS infrastructure to avoid common network problems, because I suppose everybody know the complexity to debug multicast. So if we have a VPLS infrastructure to exchanging the private keys, we could use it to retransmit the Opera itself. Okay, that is all. Thanks for your attention.
Okay, I think there's time for some questions. Do people have questions about these experiments over there? The microphone seems always to be at the wrong side of the room. But don't stand there, because then the next question comes on the other side.
I'm Andreas Polirakis from GRNet. So my question is the following. You said that Juniper uses multi-protocol BGP and Cisco uses LDP. This means that VPLS cannot work in a mixed environment with Cisco and Juniper.
Well, I don't know, because I don't test interoperability between Juniper and Cisco. Jean-Marc can ask better than me, I suppose.
Yes, that's correct. There are two drafts. One is from Curity Compeller, and the other one is from Vac Compeller, his brother Nasser. And they are not using the same protocols. The Curity Compeller draft is based on BGP, like the RFC 2547 base for layer 3 VPN. and the other one is using LDP. So it's not interoperable. But in case you want to build such services and you need to extend the service to other domains using other equipment, then the workaround solution today would be to have a layer 2 point-to-point circuit connecting two HEAnet clouds. So that's a possibility. For example, on our solution, we can take a layer 2 point-to-point Martini circuit, which is interoperable with other vendors, and connect a remote site to the VPLS domain managed by the BGP-based solution. So this way you could connect two HEAnet VPLS clouds using different protocols. So that's the workaround today. Hopefully the standardization will converge to something unique. But
okay, thank you.
Okay. Are there other questions? I have one. It's a little bit related to the scalability. I think you mentioned it a little bit. Is it indeed easy to scale this kind of things over wide area networks? Could it be possible indeed to use the LHC network? Would it be? What's your idea? Is it easy to do?
Yes, I think yes, because in the summary you can see that the general idea about the VPLS configuration is very easy. When you have the general configuration to extend this VPLS connection to the remote provider router is very easy. So you only need to establish the general VPLS configuration between domains.
And how's the maintenance going to be handled? Or let's say the troubleshooting when broadcasts are going on and that kind of things.
Everything is easy when you know how it works, no? But not really very difficult.
Yeah, can I have other comment? I think the main issue in scalability is not going to be on operational point of view, because the way you operate VPLS is exactly as you operate a layer 3 VPN, because it's using the same toolkit. Mm-hmm. So even for service providers that is using today layer 3 VPN, it's extremely easy to add VPLS or layer 2 VPN based on BGP. The scalability bottleneck would be more on the number of MAC address you want to support, because you basically need to do the same thing as a switch. That means at some point in a router, you have a MAC address that corresponds to MPLS and Lsp, right? So you need to keep that MAC address, but it's dynamic. You learn it, there is a timeout, you release, right? Okay. So this is, I think, more the MAC address aspect that could be the bottleneck. There are ways of preventing from that by using filtering capabilities in order to prioritize some flow or to manage the MAC address cache. Okay. This kind of thing.
Okay, thanks. More questions? Okay, then I want to thank you again. And I want now to give the floor to the person who already had some voice over the microphone, Jean-Marc Gouzet from Juniper, and he's going to say more about a different subject, and that's the GMPLS and traffic engineering in a multi-domain environment. So I think everybody knows how to do it in a single domain, but at least in this way we are going to see how it can be done in a multi-domain environment. Okay, the floor is yours.
Thank you, Victor. Thank you, Victor. Good afternoon, ladies and gentlemen. It's a great pleasure to be here. First of all, there was a session on GMPLS before, and here there is GMPLS titled. It doesn't mean that the scientific committee made a mistake. It's just because GMPLS is generalized MPLS, so the traffic engineering could be applied for pure packet-based network or optical network. It's the same thing because GMPLS is a superset of MPLS. Okay? So what I'm going to talk about is how the work that is done in the IETF and in order to extend the capability of traffic engineering that is well known and well used in one single domain, and how to extend it to multiple domains, what are the issues faced, and the directions taken by the IETF. So I'm going to give a word on the scope, look at some potential benefits for the RNE community, some challenges faced by this extension of traffic engineering, some requirements, the different components from routing, signaling, and other aspects. I will give a word comparing the different signaling approach because there are different proposals. Unfortunately, the different vendors or the two big vendors are co-writing the same draft, so we combine in the same draft a different approach. So I think that's good in order to progress in the standardization. And I will give some reference on the standards and the direction we are taking. So what I mean by interdomain is crossing multiple domain, and here domain can be different things. It could be an area IGP point of view, okay, so OSPF or ICS, or could be an autonomous system, and I think most of the interest for you would be inter-autonomous system. And the LSP we are talking about could be packet-based or non-packet-based, so that's why it's really GMPLS. So it could be applied to IP MPLS network or to optical SDH networks. So, for example, here this is interdomain between different areas with IGP, where the IBR router is at the frontier between the two domains. This is an example where a domain is an autonomous system, which is likely more like, what is going to be used in your environment. So it could be different national research networks and or regional networks. And here, what you can see is there is a link between two border router, which belongs to a kind of no man's land, which is something that has to be taken in account because the path from end to end will use such link. So this is something that does not exist today in the traffic engineering database. And another example could be an overlay network using an optical backbone. And in this case, you have an hybrid model where you are using MPLS packet-based LSP crossing an optical core, so with a lambda or SDH LSP. So there are different models, and all these models are covered by the draft. So today, if we look at the situation in research education networks, there is a significant usage of layer 2 circuits over MPLS. There was several examples. There is several examples of pan-European project that use the benefits of layer 2 VPN circuits to connect different sites as if they were using leased line. I think we had a session yesterday on bandwidth on demand. This is an activity that is in the GN2, and also we saw that this is an activity going on in other places in the world. So one word about comparing what we just had before the presentation from Laura, which was also about interdomain. Her presentation was about extending VPN across multiple domains by using what is defined in the 2547 bis. The topic was about exchanging VPN information and providing auto-discovery and signaling across multiple domains. Here in this draft, in this presentation, we are talking about traffic engineering. What that means, we talk about constraint-based path computation, re-optimization, and failure recovery scenario It's a lower layer activity, how you set up a circuit from end to end across multiple domains. So what are the challenges? The challenges are that we have a lack of the complete topology information in one domain, because we need to achieve scalability, and we can't imagine simply injecting all the traffic engineering database in one domain, because we would not have a scalable system, and that's the reason why we have different autonomous systems in the internet. And the other reason is also because of privacy, because a service provider or national network may not want to exchange the full traffic engineering database to another domain. Another challenge is that there is no assumptions about influencing routing and management decision in another domain. So in all cases, a domain that will receive with the signaling a request to set up a path across its domain, it has the complete control of what it's going to do with this request. So that means that apart from the signaling aspect, there needs to be some agreement policies between the domains in order to decide if they accept what they are able to accept, and also how they map some SLA components, for example, some colors or some attributes that are used by traffic engineering, or how we do we map some criteria in one domain with the other domain. And there are scalability considerations, is both at the control plane and at the data forwarding plane. We are talking about path computation issues, for example. So we are going to talk about the different components that are described in the different drafts I will list at the end of the presentation. There are routing components, reachability, topology, and traffic engineering information. There is an aspect regarding the path computation, how we calculate path from one ingress router to the endpoint, the egress router, signaling aspect, and also policies and SLAs. Regarding the routing, regarding the reachability, it's unchanged. It's based on IP, so typically we will exchange with an IGP inside one domain the loopback address, and we use BGP across multiple domains. So the assumption is that from topology point of view, there will be no leaking of any topology information outside one domain. Okay. Something that is, has to be taken in consideration and required an extension is the link that is used between two domains, which becomes a link that should be taken in consideration by traffic engineering, because the traffic engineering decision will go outside of the domain, so we need to take in account the different links that connect the external domains. So this is an information that does not exist in the traffic engineering database of MPLS, of intra-domain traffic engineering, so that had to be added. Regarding the path computation, we differentiate loose and strict hops in the hero object of RSVP message. And that means that the ingress PE router will set up a path that could be a set of strict hops, so all the hops from end to end across all domains, or could be a set of loose hops, so that we know the next hops, but there are other hops in the middle that should be calculated by the path computation algorithm. Or it could be a combination of both. So it really depends on the availability of the topology information you have. There are 3 computation options which are supported in the draft. One is to use offline management tool. So you could imagine offline management tool retrieving the traffic engineering database information from all domains and do a global and complete path computation offline, and then send to the first router, so the ingress router, the complete set of strict route that should be used by the RSVP's message to set up the path. The other approach is to use the IP reachability information you have in one domain. So basically what you know is where is the exit point, because you have BGP information telling you that the destination IP address you want to reach is in this IS, and so you have to follow this IS path, so you can deduce the loose hops. And you have the local IGP information in order to set up the path inside the domain, and in this case you can calculate the strict path. And the third option is to use path computation elements. So this is a client-server model where you can request the path to a computation element and receive the complete or partial path in order to set up your path with RSVP message. So these three computation are supported, and what the assumption is that per region there should be the possibility to compute the path inside the domain if you receive only a loose hop as a next hop. So that means if you receive in one domain and you receive a request from the other domain to set up a path to the certain loose hop, you have the possibility to expand this root object in order to add all the strict root inside your domain. Also, it has to support crankback mechanism, so that if the setup fails for any reason somewhere, you have the possibility not to calculate the complete path, but find another better route. And the path computation options are independently from the signaling mechanism, because we are going to see that there are different signaling mechanisms as well. There are basically two types of LSPs that could be set up. And it's important to consider all these types, because sometimes with GMPLS you may not have all options available. So one option is to have a single contiguous LSP from end to end. So the ingress router will set up an LSP across multiple domains, and from end to end it's going to be one single LSP. And the other approach is to use non-contiguous LSPs. So that means that in each domain you will have one LSP. And there are two approaches. The nesting approach, where you have the possibility in one domain, for example in the middle, to encapsulate several LSPs in one single LSP, which gives you the possibility to control all LSPs going from one ingress router to one egress router within one single LSP. It has some advantage. Or using the stitching method, that means that you are going to stitch two LSPs at the borders. And this is obviously something that would be necessary in case you use GMPLS with optical networks, because it's impossible to encapsulate a lambda in another lambda, right? So to do the nesting or the stitching, we use the LSP key signaling approach that was already defined before. And then there are two other aspects that are important, policies, how we map the traffic engineering constraint from one domain to another, the quality of service parameters, the authentication. Remember that traffic engineering was extended with diff-serve traffic engineering in order to take in account the diff-serve quality of service approach, which is orthogonal to the traffic engineering aspect. So this has to be extended as well across multiple domains. And there are traffic engineering related administrative actions that should be agreed, the admission control, triggering re-optimization in order to find the best path if something changed in the network. And finally, there are SLAs, service level agreement consideration, how to guarantee quality of service, providing billing and accounting, and all the settlements, how we manage this between providers. One word on comparing the two signaling approaches. If you have a contiguous LSP from end to end, then that means all the control of the LSP will be at head and label switch router. In the case we use non-contiguous LSPs, that means the LSP is built by multiple LSP pieces. Then it's hierarchical in nature, both at control and data plane. And it gives you the possibility to better manage the protection, because you know that in one domain, all LSP coming in one router or one port and going out in one port in the ingress router of your domain will go through the same and unique LSP. So you can build a secondary LSP to protect all circuits that are going from one domain to the others. And in terms of terminology, we use the the forwarding agency LSP in the nesting, and in this case you have many to one, many LSP to one LSP, and the LSP segment in the stitching mode where you have one-to-one. So let's take a couple of examples with a non-contiguous LSP. We want to set up an LSP from PE1 in the AS1 to PE2 in the AS3. So the PE1 will send an RSVP message to create a path from PE1 to PE2. And it has the possibility to calculate the strict route within the first domain, because it has all the complete traffic engineering database corresponding to the autonomous system 1. And it can add a loose hop to the next domain because it got the information to the BGP. So it's easy to create an LSP to ASBR1, which is the gateway to go to the autonomous system 2. And then in the autonomous system 2, let's consider we already have one intra-domain traffic engineering LSP, which is a forwarding agency LSP that connects the ASBR3 to ASBR5. And in case you use the nesting approach, you can encapsulate, the router will encapsulate this LSP in the existing LSP. So you don't have, for each end-to-end circuit, the need to change the setup in one transit domain. So the nesting approach has some advantage to achieve scalability in packet-based network, because you understand that in non-packet-based network, like optical network, you are not going to be able to nest an LSP in another. So in this case, we will stitch them. So here we have the nesting over a pre-provisioned intra-domain traffic engineering LSP, and the circuit goes up directly up to the exit point, ASBR5. And in the last domain, there is no existing LSP in place, so we will extend the route object with a strict route that can be calculated by ASBR7 because it has all the traffic engineering database corresponding to AS3. So we can set up a path up to PE2. And then the data path is end-to-end from PE1 to PE2. And what you can see in the last AS3, he created a new LSP between ASBR7 and PE2, but this LSP, as it's nesting the other LSPs, could be reused later by another LSP that should be created from P1 in AS1 to P2, or any other LSP that will go from ASBR7 to PE2 in AS3. So then there is the reoptimization capability. If there is a change in the topology, so let's say in AS2, a link change its characteristic or simply disappear, there is the possibility to recalculate the path. And as we are, in this example, using non-contiguous Lsp, the optimization will be done in one single domain. So in AS2, a new path will be calculated between ISBR 3 to ISBR 5, because there is a optimal path, a new optimal path. And as we are using the nesting approach in this example, all LSPs, existing LSPs between ISBR 3 and ISBR 5 will use the new LSP that was created. And there are some protection mechanisms also we have to take in account. Typically, in one single domain, we use exactly the same protection mechanism as that exists in intra-domain traffic engineering. So the issue is much more at the borders, how we manage failure if you have something broken between two domains. So it could be the link or it could be the node. If it's the link, then to protect a link, it's possible to signal a link protection backup in order to reach the ISBR router of the next domain through a different path, of course, if there is a single link that exists. And if a failure occurs, then we just use the failure recovery reroute function of MPLS, and the data will use the new LSP. And the other protection would be the node. If it's the node we need to protect, then we have to calculate a backup path that will use the next hop information you will get with BGP in order to set up a circuit that will go directly to the next hop. And in this case, the root object would be extended by ASBR4 because, again, ASBR4 knows the complete traffic engineering database in the domain AS2. So if the failure occurs in node ISBR3, then the data path will take the secondary LSP that was protecting this node. So where we are with IETF, there are several drafts, and actually not all of them are in these slides, but if you take one of these, you will find all the other reference. There are drafts dealing with the requirements. One is the LSP hierarchy, which is an important one because it's required for non-contiguous LSP. There is a draft describing the framework, the signaling, and the path computation. And also there are several proposals for the PCE approach, which is, as I said at the beginning, a client-server approach to calculate path. The approach we have at Juniper is to follow the development of the drafts in order to really closely follow the standardization, because, of course, if we talk about interdomain, the basic thing is to be interoperable with other vendors. So basically, to start with the LSP hierarchy support, inter-area MPLS traffic engineering will be first explored, so within one single IGP domain, but constituted of different areas, and then the inter-autonomous system MPLS traffic engineering. And then, based on the evolution of the PCE for path computation, then we will follow the standards. Thank you. Is there any question? Thank you.
Other questions? No, I have one,
Okay.
if you don't mind. We saw a little bit by the VPLS that the vendors choose to implement a different one,
Yes.
different implementation.
Mm.
How will that be with the interdomain traffic engineering? Do you think that both vendors or multiple vendors will implement the same standards? Or?
At least as regarding the draft we are talking about, both Juniper and Cisco are writing the same document, so they are co-writing the document. So Then I think as the standard is quite open and offer different options, it will depend on phase of development if they are aligned or not. But at least the work done in the standardization process is common, so that's good.
Okay, very good. Other questions pop up? Okay, I want to thank again Jean-Marc for the presentation. Then we have the last one of this session from Katalin about from CERN, and he's going to say something different. No GMPLS, no VPLS, no just simple Ethernet. But it's not that simple, I think. He has tried together with other people to get a very long distance Ethernet connection. I think it's 18,000 kilometers to Tokyo, so it's a long distance, and of course you can understand with all the delay and that kind of things that there will be problems, and it will be very interesting to know how to solve them and perhaps how to get better implementations or better choices of interfaces for this kind of future work. Okay, the floor is yours.
Okay, thank you very much. Good afternoon, ladies and gentlemen. My name is Katalin Meiros. I'm with CERN and the Polytechnical University of Bucharest. At CERN, I'm working for the Atlas experiment in the Trigger and Data Acquisition Group. So the point of view that I'll be expressing this afternoon is going to be more that one of a powerful user than the point of view of a network operator. So this is the overview of my talk, and I will start by presenting 10 gigabit Ethernet from a point of view which is rather different, that one of a distance independent Ethernet. And I will continue by talking about the WAN5, which is part of the 10 gig Ethernet standard. That is an option for long-haul Ethernet and SONET friendly. And here I'll present theory and results. Then I'll continue with a survey of Ethernet over transport technologies compared to the WAN5. Or if we consider the carrier environment, like the guys in suits and the guys from the local area network. It's like the scientists trying to do an experiment. The guys with the t-shirts coming with a great application and saying, look, I want this amount of bandwidth from you. This would be like a match between suits versus t-shirts, and this is round 2. So we'll see what round 1 was, when it took place, and what happened then. And I will end my talk with a question about LAN everywhere and what does that mean. On the right corner, you have a picture of the original drawing by Bob Metcalfe, the inventor of Ethernet. And this is what most of us think about Ethernet when we hear the word. It's a shared copper medium that is distance limited because of the use of the carrier sense multiple access with collision detection algorithm to decide which one of the members of the network is allowed to talk on the shared medium at a certain time, and it has limited speed. Now, what Ethernet means today is mainly represented by the 802.3ae standard in 2002, and that is no CSMA-CD algorithm, full duplex connections, point-to-point, a switched architecture for the network that supports 10 gigabit per second transmission. It allows, defined in the standard, a maximum span of 40 kilometers for the point-to-point connection over optical fiber. And the standard also includes wide area network access. So LAN-PHY over dark fiber. The 10 gigabit Ethernet standard introduces two kind of devices that can be attached to networks. One is the LAN-PHY, which was designed for the local area network, but it also includes a laser with 1550 nanometer wavelength. The 1550 nanometer wavelength, it's in the C band of the optical transmission edge, and it allows for the optical amplifiers to amplify this wavelength. So in principle, optical amplifiers could be used to increase the span of a point-to-point connection realized with this laser of the 10 gig Ethernet LAN PHY. However, from the user point of view, yes, this may happen if you happen to own the dark fiber that you are about to use, or if you manage to find a carrier that will comply to your requests for dark fiber. And in the framework of the ESTA project, ESTA, it's an acronym for Ethernet at 10 gigabit and above. It was a European project that ended this year in January. So as I said, in the framework of this ESTA project, we set up 550 kilometer long connection in Denmark on infrastructure owned and owned by THERnet, which is the Danish research network operator. And the network started in Lyngby, which is in the right low corner, and then through several optical amplifier steps and dispersion compensating fiber. These are the yellow dots in the picture. We ended the connection in Aalborg, which is in the north of Denmark, at 550 kilometers. And my colleagues measured bit error rate of 10 to the minus 12 for operation of this network, which is in the limits imposed by the 10 gigabit Ethernet standard. The results are described in a paper by Mikkel Olesen et al. And published at the COIN conference in 2004. However, there is only a certain distance that can be covered by the LAN PHY, and that is because when you use standard single mode fiber on the wide area network, at some point the signals have to be regenerated due to the dispersion compensating. But the regenerators that are deployed currently in the field, all of them only know about SONET framing of the incoming signal. This is one of the reasons why the traditional way of connecting local area networks through the internet is to use a router equipped with an OC192 interface, for example, connected to a SONET line terminating equipment, going through several stages of 3-hour regenerators, and terminating the connection on another OC192 SONET router interface. However, the 10 gigabit Ethernet standard introduces a new gateway from the local area network to the wide area network by the means of the WAN PHY, and this is presented in the picture with the green background. The WAN PHY connects to the Ethernet line, to an Ethernet line terminating equipment, and goes over 3-hour generators because the frames generated by the WAN PHY are compatible with existing regenerators because the transmission rate is the same as with SONET OC192 or SDH STM64C, and the encapsulation is the same one as used by the SONET and SDH standards. Also, the WAN PHY makes partial use of the bits of the SONET management. And in the framework of the ESTA project, we demonstrated that direct connection of the WAN PHY to both DWDM transponders and SONET SDH equipment is possible. And later in this presentation, I'll show one example of direct connection to SONET SDH. However, there are, of course, problems with the way IEEE chose to define the WAN PHY standard. First of all, the 802.3 AE standard says the optical jitter shall be measured according to IEEE specifications. Unfortunately, these specifications are different from the ones defined by ANSI and ITUT for SONET and SDH. So the question is, what happens when you interconnect two equipments that obey to two different standards? Then IEEE is used to define standards for equipment that sells in large volumes. Therefore, they are very careful about the prices of the components that enter in this equipment. So in this respect, they tried to keep the price as down as possible for the components of the WAN 5 ports, and therefore they decided to use like the cheapest clock crystal that would provide the lowest acceptable limit in terms of clock accuracy from the long-haul infrastructure point of view. This limit is 20 parts per million clock accuracy and corresponds to the degraded service SONET clock, which is only used in maintenance mode or over long-distance networks. Now, in fact, there is the standard, and then there is the reality. And for the brand new oscillators, we, in the framework of the ESTA project, developed our own WAN 5 card, and using this WAN 5 card, we measured a 0.1 parts per million difference between a WAN 5 clock and a Stratum 3 SONET clock that has an accuracy of 4.6 parts per million. However, I should warn you that cheaper crystals are expected to drift more with age. So even that in the beginning, the difference in accuracy would be minimal, then with time, this difference will increase. Another feature of the SONET SDH standard that was not supported, and it's not supported by the Ethernet WAN 5, is the SONET line timing that allows for a WAN 5 transmitter to use the incoming, the clock of the incoming signal in order to time its outgoing transmission. And this is what happens in the packet over SONET cards in routers, for example. Now, with all these things that IEEE left out of the standard, what did the manufacturers do? In fact, what they did, they used SONET optics and oscillators on the line cards of their devices, and some of them implemented line timing. And in addition, there is a recommendation from the International Telecommunications Union that says that WAN 5 can be deployed as an NNI or UNI when its clock accuracy is 4.6 ppm or better, i.e. at least a Stratum 3 equivalent. Now, using a standard WAN 5, last year in October and November 2004, we set up a circuit between CERN in Geneva and the Data Reservoir project of the University of Tokyo in Japan. This circuit had one-way latency of 262 milliseconds. And it spanned, it was crossing the domains of 4 operators: SurfNet, Canary, Pacific Northwest, and Wide. We were using equipment from Foundry in order in the local area network. Why Foundry? Because they were at the time the only manufacturer that had a Xenpack WAN 5. And then, as you see, the equipment for the long distance connection depended on the domain, on what the operators had actually installed. So it was either Cisco or Nortel. And as an example of results, here is what happens, or what happened when I ran single stream TCP using iPerf between a computer located in Geneva. It was an Opteron machine equipped with a Celsio T110 10 gigabit Ethernet adapter, and a similar machine, identical in configuration, located in Tokyo. running an iPerf using Jumbo frames and a 512 megabytes TCP window size, I was able to achieve like 7.5 gigabits per second of transfer rate. And on the right side, you can see that there were packet losses on the circuit from time to time. This was promptly seen by the TCP stack, which entered into recovery mode. And luckily, the TCP offload engine of the Chelsea adapters implemented a non-standard TCP stack that was able to recover much faster, because with a standard TCP stack, it would take more than 2 hours to get back to the transmission rate after one packet loss. And this raises the problem of buffering between LAN PHY and WAN PHY ports. Because these two are part of the same standard, people tend to forget the fact that the transmission rate of the two devices is different. The LAN PHY transmits at 10 gigabit per second sharp, while the WAN PHY only accepts a data user payload equal to 9.58 gigabits per second. So in case there is a transmitter that sends at 10 gigabits per second, there must be a buffering stage between the LAN PHY and the WAN PHY. And the graph shows the amount of buffering that would be required in order to allow given a burst of a given size. The x-axis, it's the round trip time or continuous burst interval in milliseconds, and the buffering required. So for a 260 something connection and 260 milliseconds connection and 7.5 gigabits per second, something like 20 megabytes of buffers would be required just to make the adaptation between LAN PHY to WAN PHY. One good thing about Ethernet, at least when it came to the gigabit Ethernet switches, was the fact that they could use modular optics. And the 10 gigabit Ethernet equipment followed this tradition. But where in the gigabit there were only 2 kinds of modules, we have 4 in the 10 gigabit Ethernet world today. And the first generation was the XAMPAC. This was implemented 3 of the sublayers of the Ethernet LAN model, but resulted in quite big and power-hungry devices. The XPAC and X2 somehow corrected these problems, and the third generation that is appearing today on the market is the XFP, that contains a common specification for the OC192 SONET, 10 gigabit fiber channel, G709, and 10 gigabit Ethernet. It only implements the last layer of the 802.3ae LAN model, and because of this fact, it opens the possibility of having software configurable LAN or WAN PHY switch ports, i.e. the same port on the switch with the same optics can be configured through software as to generate frames that would go either over a local area or over a wide area network. So we saw that Ethernet transmits at 10 gigabit per second and has a direct wide area network interface. But still, there are many, many limitations when it comes to deployments over long distance networks. And few examples are listed here. There's the well-known VLAN scalability, the fact that the VLAN tag in the Ethernet frame only has like 12 bits, which limits the number of VLANs to 4096. And then there is the MAC address table explosion, because an Ethernet switch used to learn the addresses of all the devices connected to a network. So what happens if you have a network that has 1 million devices? Of course, there is ongoing work to address all these limitations, And this work takes place partly in the IEEE 802.1 working group, but even more work in the ITU T Study Group 13 and in the Metro Ethernet Forum to define services and interfaces. Now, how about using link aggregation, which is part of the Ethernet technology over long-distance network? Link aggregation, it's an addition to the Ethernet standard that allows to bundle either LAN-PHY or WAN-PHY connections, in this case, together to provide a logical connection that has more bandwidth or just redundancy, depending what are you aiming at. Currently, the maximum number of aggregated links through this technology depends on the manufacturer, and it's usually between 4 to 16, translating to throughput between 40 to 160 gigabit per second on such a logical connection that provides automatic load balancing or hot standby with automatic traffic rerouting in case one of the links goes down. Okay, the time for the rerouting has nothing to do with the requirements in a carrier environment that are 50 milliseconds. But in this case, it depends on how fast the MAC layer will figure out that the link is down. In the worst case, it's 1 RTT. The long-distance networks are still dominated by SONET and SDH, as I said before. And here is a generic structure of a SONET frame. I won't give details. There's a virtual container that contains the user payload of these on these frames. And there are two methods to organize the virtual container for data-aware services. The examples below are for an STM64 frame following the G707 ITU-T recommendation. And these two methods are the contiguous concatenation, which is the encoding used by the WAN-PHY, and the virtual concatenation that creates circuits that are sum of individual VC4 containers, each container having user payload of 149 megabits per second, and each container may travel separately towards its destination. Of course, this requires a large amount of buffering to be integrated into the device that is the destination of the circuit. Because, for example, one VC4 may travel over fiber, and another VC4 may travel over satellite, and that it's a huge difference in latency. So, in addition to having this virtual concatenation, the ITU-T defined the generic framing procedure, which is a method for encapsulating variable length user payload for client signals to transfer over SDH or optical transport networks. The generic framing procedure defines a big frame, which is 64 kilobytes, that has 4-byte overhead. But it also defines how Ethernet frames are encapsulated over GFP. So there are two modes, the frame map mode and the transparent mode. The frame map mode, in the frame map mode, the preamble and the start of frame are removed from the Ethernet frame, but the flow control sequence or the CRC field are kept there. The the interpacket gap is also removed from the encoding. Now, one thing that is not obvious at the first point is that Ethernet is an asynchronous network, i.e., when a given transmitter has to transmit something, it will transmit. But when there is no transmission, there is nothing going on the line. While with SONET, even if even when the transmitter has nothing to transmit, the SONET equipment has to transmit idle characters. So if one considers the interpacket gap as a period when the Ethernet transmitter does not transmit anything, but SONET SDH is synchronous, what happens during IPG? And it's not clear from the GFP specification whether SONET idle character are put in the frame, or some generic GFP pause frames or empty frames are sent. In addition to the GFP, there's a link capacity adjustment recommendation that defines a higher layer protocol that allows for dynamically adjusting the capacity of a container. This allows, for example, to use only 5 gigabits out of a 10 gigabit connection and adjust this capacity on in service without any problem for the user. So let's go back to the suits versus t-shirts. And the first round took place in 96-98, and that was ATM, which was a technology designed for the long distance networks that tried to enter the local area network, and it had to face fast and then gigabit Ethernet, and we all know who won that contest. This time it's the other way around. This time Ethernet is trying to enter in a wide area network environment. And gigabit and 10 gigabit Ethernet have begun spreading into the metropolitan area networks. Maybe because of the fact that this is the richest area in dark fiber today. We all know that the 10 gigabit Ethernet is wide area network ready. But of course, in addition to the limitations I presented before, there are other limitations that have to be addressed before Ethernet becomes a viable technology for local area, for wide area networks. And this is first the lack of carrier grade OAM features. But a first step in this direction was done through the Ethernet in the first mile standard. Of course, there are problems with the network topology in Ethernet that are related to the spanning tree and broadcast storms. And the answer of the suits to these challenges was Ethernet over GFP, which is a long-distance transport technology that was turned friendly to Ethernet while still providing carrier-grade OAM, circuit protection, and bandwidth guarantees. So, LAN everywhere. When you think about Ethernet everywhere, does it mean that you are going to have a 100,000 node flat Ethernet network? Or how about adopting the same strategy that we see within the enterprise today? Partition the network into IP subnets. Routers have Ethernet ports. This gets rid of the broadcast storms. Ethernet as a pure transmission layer is distance unlimited and friendly to the installed base of long-haul infrastructure. And there are other interesting features in Ethernet that could be used. For example, user authentication based on the 802.1x protocol and the link aggregation that I mentioned before. Now, in conclusion, the SIU project pioneered 10 gig Ethernet demonstrations over long-distance networks, dark fiber, DWDM, and SONET SDH. I think I've showed that native Ethernet can be used to, on the long haul, to either complement routed networks using layer 2 technology if it scales to your requirements, or provide a link layer for an IP network. And the suits versus t-shirts round 2 just started with the Swiss Citadel, the wide area network, being under attack by Ethernet. These are the acknowledgements for my colleagues from the ESTA project that contributed to the work described here, the carriers that provided the connectivity, the equipment manufacturers, and 2 of the collaborators from the University of Tokyo and Carleton University in Ottawa. Thank you very much.
Okay, thank you very much for the presentation. Other questions? There's a question here.
It's just referring back to your slides where you show the problems of having a LAN-PHY and WAN-PHY interface in the same switch. So potentially you have a server connected to the LAN-PHY, transmitting at line rate, and then you have a slightly slower bit rate out via the WAN-PHY over the wide area network. Clearly one possibility to deal with that is to buffer the input when you're running at line rates on the LAN-PHY interface. One other possibility would be to, if you like, cripple the LAN-PHY slightly by inserting some type of dummy frames so that you maintain an equality of bit rate between the LAN-PHY and the WAN-PHY. Is this something that you've considered investigating at CERN?
Not to my knowledge at CERN. However, my collaborators from the Data Reservoir project at the University of Tokyo were pursuing this direction by introducing delays in the network interface card, in the packets generated by the network interface card, and spacing the packets in such way that they would not overrun the WAN-PHY.
And of the two approaches, the buffering or the artificial introduction of these delays, which do you think is the best way to cope with this problem?
Well, I would say it depends. From my point of view, as an end user, I would say leave the network interface card to deal with it. On the other hand, this will only solve the problem of a single stream or multiple streams that originate on the same machine. So maybe the solution of having the buffer do the packet spacing also makes sense. It's a trade-off of who do you want to be in control over your TCP streams.
Are there more questions? Oh. On the other side. Sorry, I hope nobody wants to.
It is perhaps a question. I'm from Noortel. I happen to be here with a pack of slides which gives some clarity on standardization work on 10G LAN mapping that might be of interest to the people in this room attending at this moment. And perhaps it's an idea to spend another 5 or 10 minutes at the end to discuss if people are interested. Or not leave, but otherwise I can do that.
Okay, thanks for that. More? I just have one, and perhaps I'm standing between something, but we once did an experiment in Ireland, which is not that big, it's only 200 kilometers, I think, but it was only 1 gigabit on one side and another gigabit on the other side. We only used pings, no FTPs. So we, and then multiplying the pings by having the ITT. So we could easily make a 1 gig stream. The problem was that we got errors because one of the basic problems with Ethernet is that the clocks are not synchronized. So your clock on the sender side can be different than on the receiver side. The sender is faster than the receiver. You get automatically drops and that kind of things. We got losses. That's inherent in Ethernet. And that's already, we saw that with 1 gig links. Do you think that problem also exists in 10 gig links? Is it worse or is it better because of the accuracy of the clocking, or what is your idea?
The clocking of the 10 gig in terms of WAN-PHY is much better than the clock of the LAN-PHY. The clock of the LAN-PHY is specified to 100 parts per million, while the clock of the WAN-PHY is 20 parts per million. So it's much more accurate. Now, the problem still exists. And I would say it's somehow lower in the 10 gigabit Ethernet than in the gigabit Ethernet because of the fact that, for example, the interpacket gap on the 10 gigabit Ethernet may be modified on the fly, which is not allowed in the 1 gig standard. Now, whether a device would be built in order to take advantage of this, that's a completely different story.
Okay. Okay, thanks for that explanation. More? And I would like to thank everybody again for being here. I just have one remark before leaving. Perhaps everybody knows that online you can fill in the user questionnaire. A lot of people got lots of mails with codes to get access to it. Use only the last mail you got, and that is the best one to use. So use the last code you got in these mails. So thanks very much.